Let's think about where we're going. It's been about a few months since I started into this quantum computing and so on, April to be exact. We've covered a lot of things. And now we're down, I've got this thing on the screen called ATP, which is, I'll read it off, adenosine triphosphate. What is that? What has that got to do with quantum computing? Let's remember, quantum computing is a really good analog of real atomic level actions. And atomic level actions are chemistry, essentially. One of the problems that is very possible to be solved with quantum computers once they get to larger number qubits with fault tolerance, then we can do things that you couldn't do before. And one of those things we can't do now and we desperately want to is solve this nitrogenase problem. And nitrogenase involves this ATP. I'm not going to try to pronounce it again. That's why they just use the initials. Is the power or the energy that comes to break the nitrogen atom and create pneumonia. Not pneumonia, that's funny. Create ammonia, not pneumonia. Okay, maybe I'll get pneumonia by going over these videos. That has the energy. So we're going to try to break it down into areas so I can understand it and you can understand it. And what I've got on the screen now is this molecular form to all this. Now let me break it down into these areas, which I have done before in earlier videos, but we've got to keep going back to this until we finally understand the structure. This is amine up here. And the amine is what we need for, really not the energy. That's just the way this thing is built. So the amine doesn't really change. The glucose sugar doesn't really change, but when we transfer the energy, one of these phosphates, in particular this phosphate, gets pulled away from it, and when we pull that away, it actually has some repelling action between the other phosphate, so that kind of springs it away, and that gives us some additional energy. Let's talk about where does the ATP come from. It's inside the cell, and in that cell we do this process called glycolysis. The mitochondria are bacteria-like organelles in the cell of a plant that produce this ATP. Here's where the energy happens. ATP plus water creates this ADP plus an extra phosphate. Remember I said we're going to strip a phosphate off here? Well, that phosphate that gets stripped off, there it is. Here's this other phosphate over here, plus a proton. So what's different about this? This is the same, and this is the same. So the amine and the glucose sugar are the same, and the only thing that changes is when water gets involved, it has enough forces involved to strip away this phosphate, but then take advantage of the repelling action that it had already. So really, once this thing is in there and tied together, it has, like a compressed spring, is ready to come off. But there's forces that overcome that compression of the spring. I love this diagram. Here's the starting energy, and here's the ending energy after we get through with all of this. So in a way, it's like we're increasing energy. Here's water. And then by the time the phosphate springs away, we're down here. So what's the difference between this line and this line. There's the ATP energy stretch, and we can take advantage of that to do some chemistry and eventually break one of the nitrogen gas bonds so we can make ammonia. Now here's another diagram. Here's the ATP hydrolysis that we talked about. Hydrolysis means that it's just combining with water. And down here we're electron transfer that weakens the triple bond of nitrogen so that we can get to ammonia. So what the heck are these proteins doing? What are the proteins doing that we want to see what's going on? If we didn't have these proteins around, then this would just be expressed as heat, vibrational areas of the molecule. The proteins are inside the catalytic molecule, iron molybdenum cofactor that we have talked about before, but this is where that comes into play. Without this, we can't take advantage of that energy and come down and do this process down here. The electron transfer comes from this conformational change, meaning that there's different kinds of ions that can be created from iron. You can have a +2 ion, or you can have a +3 ion, and between those differences we come up with an extra electron that then can be used in this process of forming the NH3. And each time we have to go through a cycle 8 times until we get 8 electrons, and that comes up with transfers into 8 hydrogen protons. In other words, they're just H plus ions, and those create the hydrogen phosphate thing from the ATP to ADP. That's a mouthful, and you might want to run that back, or you might not.